Hi all, we're doing this review game in class and I needed to make the key, so I figured I might as well make the video and talk through it in case anyone is wanting to use this to review for the test. This first 50 question review game covers units, or I really should say has questions from units 1 through 6. Okay. So some of these I'm going to talk through more, some of them I'm just going to go more quickly. So the mass spectrum of a sample of a pure element is shown above or below. Based on the data, the peak at 26 AMU represents. Okay, so we have this right here, aluminum, magnesium, iron. The average atomic mass of these three is what we would see on the periodic table. So I know that my average atomic mass, on average, when I consider each parts of these, this one is the most abundant. This one is this is the least abundant. So on average, I would be to the right of 24, right? Maybe to 25, but I'm somewhere in here would be my guess. Now, aluminum has an average atomic mass of 26.9, practically 27 all the way over here. So that would not be aluminum, right? This would not be the mass spectrum for aluminum. Magnesium has a mass spectrum of 24.3, and so that's a potential answer. That's reasonable. Iron is 55. It's definitely not that. And then RTI. Maybe you guys will find it faster than me right there. Where's that RTL? Either way, right there, 47.8. That's definitely not that. And so it has to be magnesium. Now, the number of neutrons doesn't really matter, but I will say the mass number, each isotope, there must be 3 different isotopes of magnesium. Magnesium 26 would be this guy, and that's what the mass number is. It'd be a mass number of 26 for that little blip right there. Mass number is equal to the number of protons plus the number of neutrons. And magnesium has 12 protons, and we know the mass number that they're indicating is 26. And so then that would require the number of neutrons to be 14, like we see in the answer there. Okay, number 2. After completing an experiment to determine gravimetrically, a reminder that just means by mass, like measuring, putting it on a scale, the percentage of water in a hydrate, a student reports the value of 38%. Okay, the percentage of water in the hydrate. So a hydrate is something with water, okay, with H2O. The correct value is of the hydrate, of the percentage of water in the hydrate is 51%. Okay, so we got 38, but it should have been 51. So we were incorrectly low. So we got to think of something that would give us a percentage of water that would be lower than the anticipated value. And so thinking about that explanation, a strong initial heating caused some of the hydrate sample to splatter out of the crucible. Reminder, how this works is we get a crucible and it's got the hydrate and it's got the water in there. And if some of this solid splattered out, we would have perceived it as water because we heat this thing up and what leaves is the H2O. So if other stuff leaves and we don't notice it, we would have perceived it as water incorrectly. That would have given us a percentage of water that is higher than what it actually is, not lower. The dehydrated sample absorbed moisture after heating. Same idea. So if we absorb water, we would have perceived it as the hydrate that was left in here, right? The idea is that supposedly when we're done heating, we're left with a hydrate and all the water would have left already. Okay, so if something got back in here and was making this way more, that would have incorrectly given us the perception that this was more and that was less. So that would give us a lower one. The amount of hydrate sample used was too small. That wouldn't make it bigger or smaller. The crucible was not heated to a consistent mass before use. So there would have been some water left in there, and that would have given us a higher percentage. So the idea is like, here's my empty crucible, and if I have some water droplets on the side, I want to heat this multiple times so I can get the water to leave. Well, if there was some water in there, and then I add the hydrate with the water, then extra water would be leaving. That'd give us a higher percentage. The excess heat caused the dehydrated sample to decompose. No, that doesn't make sense. All right, so B. A solution of methanol, CH3OH, in water is prepared by mixing together 128 grams of methanol and 108 grams of water. What is the mole fraction of methanol, okay, of the CH3OH? Okay, great. Mole fraction of something is when you get the moles of the item, this time it was methanol, divided by the moles total. That's how I get a mole fraction. It's not a percentage, it's a fraction, so I don't times this by 100. So we have 128 grams of methanol. And we have 108 grams of water. And I need moles of both of these things. Okay, so methanol is C, so carbon 12.01 on the periodic table, plus hydrogen 1.008 times by 4, because there's 4 hydrogens and 1 oxygen, which is 16. So this is 32.042 grams per mole. That's roughly 4 moles of the methanol. And then this should be 18.015, but I always get it. I mean, it doesn't really matter. 1/6 with this periodic table. So then 108 divided by that number gives us roughly 6 moles of water. Okay, so the moles of the methanol was 4. And the moles total is 4 plus 6, so 10. So that'd give me a mole fraction of 0.4. Which of the following represents the ground state electron configuration for Mn3+? Well, the easiest way to do this is starting with just the manganese, just Mn. Okay? So as I go through my periodic table here, I'd have a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 3d5. Okay, I'll write that down really quick. Okay, great. Now, in order for this to become a 3+, we have to lose 3 negative electrons. They're going to come from the highest electron shell first, and that is the 4th one there. There's 2 electrons there I'm going to get rid of. That would make it a 2+. Now I need to get rid of 1 more, and I'm going to go to the next shell, which is 3. So I have a 3s2, 3p6, 3d5, so spd. So I'm going to take 1 from there. So I would end with a 3p6, and then, oh, I don't want any of the 4s. That one has a 4, that one has a 4, that one has a 4, so it's got to be this answer. 3p6, and then 3d4. Okay, number 5. The complete photoelectron spectrum of a pure element is shown in the diagram above. According to the complete photoelectron spectrum, which of the following is the identity of the element? Now, for electron spectrums, the first thing is I need to check my x-axis here and see where energy is the highest and where it's the lowest. Typically, they have the highest on the left and the lowest to the right, which is unusual. But the reason why is because the electrons that are closer to the nucleus require more energy to pull them away. So what's nice about this is when energy is highest to the left, then that's our 1s peak. And the height is how many electrons. So we know that this is a 1s2, and that must be the height of 2 electrons. So then we have 2s2 and then 2p. But how many electrons? This is the peak for 2, so 2, 4, 6. So we're ending with 2p6. So here's energy level 1, here's energy level 2. Here's 2s, here's 2p, and then 1, 2, 3, 4, 5, 6. So that would be neon. Which of the following lists magnesium, phosphorus, and chlorine in order of increasing atomic radius? Magnesium is right here, and then what's the other ones? Phosphorus and chlorine. Oh, okay. So they're all in the same period. All right, now this is where students get it mixed up. When atomic radius gets bigger going down because we get increased number of electron shells. Going to the right, though, it's all in the same shell. And even though the mass number is getting bigger, the atomic radius actually gets smaller going from left to right, and that's because the number of protons pulling on the outside electrons increases. And so it has a stronger attraction pulling those electrons in closer to the nucleus. So chlorine of these three would have the smallest radius, then phosphorus, and magnesium would have the biggest. So magnesium would have the biggest, and then chlorine would have the smallest. Based on the ionization energies of element X given in the table above, I guess to the left, which of the following is most likely the empirical formula of the oxide of elements? So ionization energy is how much energy it takes to remove an electron. And when it comes to successive ionization energies, I'm looking for where the biggest jump is. And I see a huge jump in this energy between the third and the fourth. So what that means is that this atom, however many rings it might have, it must have had 3 electrons in the outside ring, 1, 2, 3, and then we had a big jump of energy before we go into the next ring there. So if it has 3 valence electrons, this is 1 valence electron, 2 valence electron, 3 valence electrons. It's one of these group 13 elements. Either way, this element X that's in group 13, if it has 3 valence electrons and it loses those 3, it becomes a 3+, right? Anything in group 1, when it forms an ion, it becomes a +1. Group 2 is a +2. Group 13 is a +3. 18 doesn't tend to form ions, and then 17 -1, 16 -2, 15 -3. Oxygen is in group 16, it's a -2. So if we have this metal X, which is a 3+, and oxygen, which is a 2-, and then we crisscross those charges for the subscripts, then that should be our empirical formula. Which of the following substances has a bond with the greatest ionic characteristic? Okay, we have covalent, ionic, and metallic bonds. Covalent bonds happen between a metal and a non-metal. Okay? And so we get our transition metal line right through here. To the left of that, excluding hydrogen, these are metals. To the right are non-metals. So if we have a metal and a non-metal, that would be ionic. Sorry, I think I might have said covalent before. That's ionic. A covalent bond is between 2 non-metals, so 2 guys over here, and a metallic bond is between 2 metals over here. So the one with the greatest ionic characteristic, first I need it to be a metal and a non-metal. And if I have multiple of those, I'm going to look for ones that are further away from each other, because that would be a larger difference in electronegativity, where electronegativity is the biggest with fluorine, and then our, noble gases, but smallest over here. Okay. Now, I have carbon and chlorine, those are two nonmetals, so no. Copper and chlorine, that's a metal and a nonmetal, so that's a possible answer. Calcium and chlorine, that's a metal and a nonmetal, that's a possible answer. Nitrogens and chlorines are nonmetals. So here is my copper and my chlorine, and here's my calcium and my chlorine. Calcium and chlorine are further away. They have a greater difference in electronegativity, so they would have a greater ionic characteristic. Okay, number 9. The energy required to dissociate an ionic solid into gaseous ions, lattice energy, like how much energy it takes to pull them apart, essentially. For the compound of sodium fluoride and magnesium fluoride is shown in the table above. On the basis of Coulomb's law, which of the following best helps to explain the large difference between lattice energies? All right, so when it comes to ionically bonded things, not covalently bonded, ionically bonded. These are metals and nonmetals that are ions, and it's a positive cation and a negative anion, and there's an attraction between them. That attraction is based on two things. Like if we compare these two items, then we can make good comparisons between the strength of this attraction. The first one that is way more important than the second one and will outweigh the second one is the charge of these ions. The second thing, if they all happen to have the same charges, is the radius. So the higher the charge, like the greater magnitude of the charge, the stronger the attraction is between these ions, the more energy it would take to pull them apart. The larger the radius, the weaker the attraction between these ions. So we have sodium and fluorine. Sodium is in group 1, so we know it forms ions with a +1. Fluorine is in group 17, so this is a -1. And then we have our magnesium and fluorine. This is a 2+ and this is a 1-. Okay, so, or -1. This is also a 1, not that it matters. They're not the same charges. They're not the same magnitudes of charge. So that's where my focus is going to be. Because this is a +2 compared to a +1, this will have a greater attraction to the fluorine. That's why this is such a larger lattice energy. It takes more energy to break this apart. Okay, so now looking at this, the charge of the magnesium cation is larger. So that's our reason. Again, if they happen to have the same charges, then I'd be looking at radius. We talked about this already, but atomic radius increases as we go down the group, and it decreases going from left to right. And the one that had the smaller radius would have the greater attraction between those ions. Number 10. To make gold stronger and harder, it is often alloyed with other metals. Okay. So, reminder, there are two main types of metal alloys. The first one is substitutional, and the second one is interstitial. Substitutional happens when these metal atoms, or metal mixed with something, maybe another metal, maybe something else, when those atoms are comparable in size. So, like if the gold is similar in size to the copper, then it would be a substitutional alloy. We're talking atomic radius, not mass. Now, next, interstitial alloys are different. Interstitial are when the radii are not comparable, when one is bigger and one is smaller. When that happens, the smaller one can kind of fit in the spaces around the bigger one, and it tends to make metals stronger because we're just getting more of that contact, more of that attraction. And then it tends to be more brittle as well. Yes, stronger, but also more brittle. All right, so let's continue on. Consider two alloys, one of gold and copper and one of gold and silver, each with the same mole fraction of gold. Okay, so gold is in both of them, and one time it's mixed with copper, one time it's mixed with silver. Now notice that the radius of the gold and the silver are identical. So that mixture is going to be substitutional, where the gold and the copper are not as comparable, right? So this gives us more of those interstitial characteristics. This is more of like, so this would be a stronger one right here. And then we'd also have be more brittle as well, that mixture. Okay, let's see what it goes on to say. Then if the gold and the copper alloy is harder, so stronger, than the gold and the silver, then which of the following is the best explanation based on the information in the table above? Okay, we want radius. Yeah, the copper atoms are smaller than silver atoms, thus they interfere more with the displacement of atoms in the alloy. Thus they interfere more with the displacement. Yeah, we're talking about size, so that must be our answer. I kind of got stuck with the interfere more with the displacement. They get stuck in the little spaces easier, right? They're smaller, so they can kind of fit into nooks and crannies easier between those atoms. The electron dot structure, Lewis structure, for which of the following molecules would have two unshared pairs of electrons? Okay, I'm going to show you how I do a couple of these Lewis dot structures, and then we're going to use the same concept to quickly do the other ones. First thing is I'm going to make a skeleton structure, and nature tends towards symmetry if possible, so I'm going to put sulfur in the middle, hydrogens on the outside. Hydrogens are unique because they want a duet, not an octet, that they're happy with just sharing the one electron that they brought. Okay? And so here, we know that hydrogen, 1 valence electron, 2 valence electrons, 3, 4, 5, 6, 7, 8 valence electrons. So these hydrogens each brought those 1 valence electrons, so those ones are good. Sulfur, on the other hand, had 6 valence electrons, and we've only accounted for 2 of those 6. So let's add the other ones in. So this is 1, 2, 3, 4, 5, 6. We don't have any free radicals, that's unpaired electrons. When we have unpaired electrons, we try to partner them up with other electrons to make double bonds. Okay. This also has formal charges of 0, like hydrogen, when it's neutral on the periodic table, it has 1 valence electron and it's assigned 1 valence electron. So those are formal charges of 0. Sulfur on the periodic table has 6 valence electrons, and here it's been assigned 6. 1, 2, 3, 4, 5, 6. And we know when formal charges are closest to 0, that's the likely structure of this. It's a valid Lewis dot structure. So which of the following molecules would have 2 unsharing pairs of electrons on the center? This one. We got our answer right away. These are a shared pair. This is an unshared pair. So here's the unshared pair, here's an unshared pair. So we have 2 unshared pairs. Okay, great. If you want to practice doing Lewis structures, you can. Again, so many of these have hydrogen, so that's easy. Nitrogen has 5 valence electrons. We've used 1, 2, 3. So there's 4, 5, so it has 1 unshared pair. Carbon and 4 hydrogens. Carbon has 4 valence electrons. We've used all 4, so that's a happy structure. HCN. Now, when they don't tell us which one in the center is, we can assume that the formula is probably telling us the combination, right? Which atoms are bonded to which. So this is an interesting one because nitrogen has 5 valence, and so we have 1, 2, 3, 4, 5. Okay. Carbon has 4. 1, 2, 3, 4. Now, normally I'd start by pairing them like this, but I guess I could partner those guys. 1, 2, 3, 4, 5. 1, 2, 3, 4. Suboctet on the center on the carbon. Yeah, I think that's a valid structure. I think it's uncommon. I think normally we would take these two here and these two here and turn them into a bonded pair. This would satisfy the octet rule. So everything now feels like it has 8. Yeah, this is better. Because in both of these, we have formal charges of 0 across the board, and we satisfy the octet rule as well. The octet rule is not as telling, as important as formal charges usually. But if we can make both work, then that's great, because see how this nitrogen has 5 assigned to it, 1, 2, 3, 4, 5, and this carbon has 1, 2, 3, 4, just like the period balance, just like the periodic table when it's neutral, and the hydrogen has 1. Okay, and then CO2 ends up like this. Oops, double bond oxygen. So that doesn't have any lone pairs on the center. Okay, next. Which of the following Lewis diagrams best represents the bonding in the N2O molecule? Formal charge. Okay, like I've been telling you. Formal charge is a comparison of when the number of electrons assigned to a neutral atom on the periodic table, valence electrons, compared to what's assigned to it in this molecule. So nitrogen is in group 15. That means it has 5 valence electrons. And this first structure, we're assigned 1, 2, 3, 4, 5, 6. This one has an extra electron compared to the periodic table. So this would mean that it has a formal charge of -1. It has an additional negative electron. This is a +1 because it has 1 less electron than we anticipate that it would. Okay? That nitrogen on the periodic table has 5 valence electrons, but here it's assigned only 1, 2, 3, 4. So it's 1 less negative electron. Oxygen has 6 valence electrons on the periodic table, and in this structure it's assigned 1, 2, 3, 4, 5, 6. So then that would be a 0. Okay, so I'm just going to do these formal charges really quick. Okay, now this is definitely not it. The closer we can get to zeros, the better. And even if there's like a +1 and a -1, I would take this over anything that had a 2 in there. So right away, it's like these are not it. But both of these structures, the first and the second, have formal charges of 0, +1, and -1. And so the last thing to go with formal charge is the more electronegative atom with the more negative formal charge is the more stable. So we have a comparison of the -1 either being with the nitrogen or being with the oxygen. Electronegativity is the biggest with fluorine. Oxygen is closer to fluorine than nitrogen is. Oxygen is more electronegative than nitrogen is. So if we can get that -1 formal charge to be with the oxygen, that's slightly more likely to happen than with the nitrogen. This makes this a slightly better, more stable structure. Number 13, which of these molecules contains 1 sigma and 2 pi bonds? Okay. The first couple that I can throw away right away. Lithium is a metal, so we're talking 2 metals here, so these are not covalent bonds. We would need non-metals. So this is like sea of electrons kind of deal, not covalent bonds. Boron is a transition metal, so that's also a questionable one. I'll come back to that if I'm not sure on the others. So we have these diatomic molecules. And I could sit and I could count valence electrons and move it around until I'm obeying the octet rule and I have formal charges of 0. They also have a little trick that I use. If I have 2 atoms covalently bonded and they're both from group 17, this will be a single bond between them. If it's group 16, 2 atoms from 16, it'll be a double bond. And if it's 2 atoms from 15, then it's going to be a triple bond. This will satisfy the octet and give formal charges of 0. So nitrogen is triple bonded. Oxygen is double bonded. And fluorine is single bonded. Okay, reminder. If I have a single bond versus a double bond versus a triple bond, all 3 of these have 1 sigma. 1 sigma bond. And then the rest of them are pi bonds. So this single bond is a sigma bond. This double bond is 1 sigma and 1 pi. And the triple bond is 1 sigma and 2 pi. And that's what we're going after, is the 1 sigma and the 2 pi. So we need the triple bonded one, so that would be the nitrogen. In the reaction represented to the right, but we're talking about this guy right here, what is the hybridization of the carbon? Okay. Hybridization has to do with steric number or number of domains. So just a reminder, a domain, or what would count as a steric number, is the amount of electron domains around the center. And a domain can either be a bond to another atom, single, double, or triple, or it can be a lone pair. So example, this carbon right here, it has 1, 2, 3 bonded atoms around it. I don't care that this is a double bond. There's 3 bonded atoms around it, and there's no lone pairs on this carbon. That means that that carbon has a steric number of 3. Same with this carbon. It's a steric number of 3. Now this carbon over here, we have 1, 2, 3, 4 bonds around it. Carbon has 4 valence electrons, and so it doesn't have any lone pairs. 1, 2, 3, 4. They're all accounted for. So there's no additional lone pairs on here. So this would be a steric number of 4. There's 4 bonded atoms, no lone pairs. It didn't ask for this, but the steric number on this oxygen, oxygen has 6 valence electrons, and we're only accounting for 1, 2. So this would be 3, 4, 5, 6. This oxygen also has a steric number of 4. 2 of them are bonded atoms, and 2 of them are lone pairs on the center, for a total of 4. If we have a steric number of 1 versus 2 versus 3 versus 4, then our hybridizations change but have a pattern between them. So they all start with S, and it's a single S, like 1S. And then we add p orbitals as needed. This one doesn't need a p orbital. So p orbital, p orbital, p orbital. So steric number 1 has a hybridization of just S. Steric number 2 needs both an S and a p. Steric number 3 is sp2. And then steric number 4 is sp3. Okay, for a total equaling the steric number, because this is a single s orbital, so that would be a steric number of 1. This is a single s orbital and a single p orbital. Add them together, I have a steric number of 2. This is a single s and 2 p's. Add them together, I get a steric number of 3. All right, great. Just like when we do our electron configurations, 1s2, 2s2, 2p6. So we go from s to p. Okay. Now, here we had a steric number of 3, so that would be an sp2, to a steric number of 4, which would be an sp3. So the correct answer is D. Okay, next. 15. The structural formula for the 2-isomer of 1,2-dichloroethene are shown above. Great. Now, looking at this, because I remember this question, they're asking about vapor pressure. So, quick reminder, boiling point versus boiling point, melting point, and vapor pressure. Okay, so if I have a stronger IMF, this is directly proportional to boiling point. This is directly proportional to melting point, but it is inversely proportional to vapor pressure. The higher the IMF, the lower the vapor pressure, or vice versa. We could say lower IMF is lower boiling point, lower melting point, higher vapor pressure. All right. Looking at this guy right here. This is cool. It's symmetrical. So it definitely has London dispersion because it's a molecule. So these both have London dispersion. Because these chlorines are on opposite sides from each other and the hydrogens are on opposite sides from each other, it's not a polar molecule. It's nonpolar. So it has only London dispersion. It doesn't have dipole-dipole and it doesn't have hydrogen bonding. Now, because these are not opposite from each other for the cis side of this isomer, they can't cancel each other out. The pole of the chlorine cancels with the pole of the chlorine, where here they can't cancel. Okay. Now, this would make it asymmetrical. This would be polar, so it also has dipole-dipole. So if this is my stronger IMF, then that's my lower vapor pressure. If this is my weaker IMF, then that's my higher vapor pressure. All right, great. So let's see. We're wanting to know about vapor pressure. This isomer, oh, it went in the higher vapor pressure. So the trans one, cis is trans, okay. So here's the two that are trans. Answer option C, the trans isomer, because it has a dipole-dipole interaction. No, it doesn't. It has a London dispersion, not a dipole-dipole. Answer option D, the trans isomer, because it has only London dispersion. Yep, that's it. Weaker IMFs, higher vapor pressure. 16. Based on Coulomb's law and the information in the table to the right, which of the following cations is most likely to have the weakest interaction with adjacent water? Okay, so it's an ion-dipole interaction because water is polar, so it's got a dipole, and then these guys are ions. The Coulomb's, the two factors that affect the attraction of an ion is charge and radius. So the greater the charge, the greater the attraction. The smaller the radius, the greater the attraction when it comes to ions. Okay? So this is weakest. We want the lowest charge, and we want the biggest radius. So these two have my lowest charge. Lithium and sodium. Reminder, as you go down the group, the radius gets bigger. As you go from left to right, it gets smaller. So sodium is bigger than the lithium. So if it's bigger, then for ions, that means a weaker attraction. That's not true for molecules, people. Ions, positively and negatively charged things. The smaller the radius of the ion, the greater the attraction. So the larger the radius, the weaker the attraction, and that's what it was asking. It wanted the weakest one. So that means our answer is B. The diagram to the left represents a particle in aqueous solution. Which of the following statements about the particle is correct? Okay, look at these water molecules. Hydrogens have lower electronegativity than oxygen. So that means these dipoles are pointing towards the oxygen. So hydrogens are our partially positive sides, and the oxygens are our partially negative sides. So all of these positive hydrogens are surrounding this thing. This must be negative then, because we get that attraction between the positive and the negative. So the particle must be a cation. No. The particle must be an anion. Maybe. The charged particle cannot be determined. The charged particle. Okay, so then our answer is B. The particle must be an anion because the positive end of the water molecule is pointing towards it. 18. A 0.2 mole sample of magnesium chloride and a 0.1 mole sample of potassium chloride are dissolved in water and diluted to 50 milliliters. What is the concentration of the chlorine. Concentration is moles of the thing, so moles of chlorine ions divided by the volume total in liters. Okay, liters. So I need those two things. I need the moles of the chlorine, and I need the volume in liters. We have a 0.2 moles sample of magnesium chloride. Okay? So 0.2 moles of magnesium chloride. Well, guess what? For every 1 mole of magnesium chloride, there's 2 chlorines in there. So that would be 2 moles of chlorine. So whatever the moles are for magnesium chloride, it contains twice as many moles of chlorine. But that's not all of it. We also had a 0.1 mole sample of potassium chloride. For every mole of KCl, there's only 1 chlorine in there, so it's the same amount of moles of chlorine. So my total amount of moles of chlorine is 0.4 plus 0.1, so we have 0.5 moles of chlorine, divided by 500 milliliters, but we need it in liters, so divide by 1,000 or move the decimal place 3 times. So we get 0.5 liters. Well, 0.5 divided by 0.5 is 1, and the units is moles per liter, or molarity. Number 19. Equal volumes of solutions in 2 different vessels are represented to the left. If the solution represented in vessel 1 is KCl, notice this is a 1-to-1 ratio for the ions there. Then the solution represented in vessel 2 could be an aqueous solution of. Okay, so positive ions, negative. So potassium is my metal. Metals form cations. So that must mean for this guy there's 1, 2, 3, 4 potassiums, and there's 4 chlorines. This makes sense because if you reduce that down, we get a 1-to-1 ratio. Now in the other one here, we don't know what it is yet, but we know that our metal, which could be potassium or calcium, so I'm just going to do M for metal. We got 1, 2, 3, 4, 5, 6, 7. We got 8 of those, twice as many as in the other one. And then our chlorine, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, we got 16 of these. Oh, so this is an 8-to-16 ratio. So it's a 1-to-2 ratio. So that narrows us down right here. So this has to be calcium chloride. Okay. How many combinations of KCl do we have in this volume? We got 4 of them, right? 1 potassium and 1 chlorine. So if there's 4 in this given space, that's whatever its concentration happens to be. Now, for the calcium chloride, we have twice as many of these combos. We have 8 of them. So the concentration is double over here because we have twice as many combos of this. So it's CaCl2 with twice the molarity as the solution in vessel 1. Okay, 20. All right, now here's what you need to remember about chromatography. Whatever the liquid is, you need to check if it's polar or nonpolar. And then remember, likes dissolve likes. So if something travels with the liquid, it's similar to what the liquid is. If something doesn't travel with the liquid, it's different than what the liquid is. You guys are so used to water being the liquid that's then going to be traveling up the paper. Be conscious of the direction of flow as well. That's polar. Water is polar. But hydrocarbons, molecules that are made up of only hydrogen and carbon, those are nonpolar. So this guy is nonpolar. So then as it was traveling up the paper, X traveled way more than Y did. So that means that X is more similar to the liquid, the hexane. So X is probably nonpolar and Y is probably polar. Okay. the answer option's kind of pulled over here. I'll try to fix that before I print it for you guys. So let's see. X has a larger molecular mass, so that doesn't matter. X is more polar than Y. Nope. Y is more polar than X. D. So we got these structures here, and we're saying how do we get increasing solubility with water? Likes dissolve likes. The more similar something is to water, the more soluble it is with water. And there's two things I want you to consider. First is water is polar. So if I'm comparing something polar to something nonpolar, something polar is going to be more soluble in water than something nonpolar. The other thing to consider is that water has hydrogen bonding. And this hydrogen bonding, there's more than one place that the hydrogen bonding can occur. So hydrogen bonding can happen like over here, and it can happen over here, even technically right there. So we have multiple locations for hydrogen bonding. So looking at this, our first option is a hydrocarbon. So this is nonpolar. So that's going to be the least soluble. Now both of these have little hydroxyl, little OH groups on them. So these are both polar. They're both similar to water. This one has one location for hydrogen bonding. This one has two locations. That makes it really similar to water. These like two hydroxyl groups essentially. So this one is more similar, so it's the most soluble. So that would mean Z is the most soluble, Y is the least. Or sorry, X is the least. Okay, it's been a hot minute since we talked about this one. So we have our ultraviolet, our infrared, and our microwave. Okay, so microwaves are less energetic than infrared. Infrared is less energetic than ultraviolet. So most energetic to least energetic. If a molecule absorbs this lower one, then it can cause, is it the vibrations or the rotations? I think it's rotations. It can cause a molecule to rotate where it's at. Okay? Like it doesn't take a lot, it just causes it to rotate. Now, if we absorb something a little bit with a little bit more energy, infrared, now it can vibrate. Now we can move across, not just spin. And then if we absorb enough energy, the electrons inside these molecules can make electron transitions. Bonds can even be broken from this. And so that's what it associates with. So region Z is our rotation one. Right there. And then Y is our vibration, and then X is our electron transitions. Okay. Which of the following is the closest frequency of light to a photon with an energy? So our energy is 3.3 times 10 to the negative 19 joules. We're trying to solve for frequency. So we have energy and we're trying to solve for frequency. Okay? And so if we have Planck's constant, we can do this, and guess what? Planck's constant is given to us. So we're solving for frequency. Planck's constant, 6.626 times 10 to the negative 34 joule seconds. And the equation that we just saw on the blue reference sheet was Planck's constant times by frequency equals energy. So to get frequency, we would take that energy and we would divide it by Planck's constant. So I'm going to be really careful with parentheses. There's my energy divided by Planck's constant. .9, so essentially 5 times 10 to the 14th. Okay, 24. Now, before I read all the text, I'm jumping to the end. I want to know what the question is. The question is, which of the following is most likely to is the most likely explanation for the variance of the data point at 6 molarity? That data point is higher than it should be. And I see that my y-axis is absorbance. So this solution, has absorbed more light than anticipated. And we got to think of a reason for why it would make that mistake. What has happened? What error has occurred? So answer option A says the cuvette. Reminder, that's the little square containers that we put the liquid in them, and then we put them into the spectrophotometer, and it sent light, and then it would absorb some of that light, and like less of it would come out on the other side, and that's how it was measuring the absorbance. So the cuvette into which a 0.6 molar solution was placed had some water droplets inside of it. That would lower the absorbance. And here's why. If I have some water droplets and then I add my solution in there, it dilutes the solution. And so if it's diluted, then it absorbs less light. The cuvette into which the 0.6 molar solution was placed was filled slightly more than the others. That wouldn't make the absorbance higher or lower. The wavelength setting was accidentally moved away from maximum absorbance. So if it was moved away from absorbance, then that would cause a lower amount of absorbance. So it's not that one, so process of elimination, but it does say the cuvette used for the 0.6 molar solution had not been wiped clean before putting it in the spectrophotometer. So like I placed this in here and I had my thumbprint on there. Like I touched this and I deposited items onto the surface. So then this light could be absorbed by those items as well as the solution. So that would cause a higher absorbance. That's what we see as a higher absorbance. 25. A 20 milliliter sample of 0.5 molar HC2H3O2. Okay, now right away, I'm assuming this is an acid, and it's not one of my big 7 that I need to know, so it's a weak acid. And I'm titrating it with sodium hydroxide, which is a base. And this is a strong base, and we recognize that because it's a group 1 metal and hydroxide. Great. Now, which of the following is the best representation of the species that reacts? Oh, species that reacts. Okay. That's one of those special phrasings that I want you to read and be like, oh, I know exactly what this is trying to ask me, and it's net ionic. If there's any spectator ions, I want them to cancel. But if they don't cancel, then I want them to be there. Those are those species that actually react. Okay. These are both aqueous. But only strong acids and strong bases break apart when it's aqueous. So this HC2H3O2 aqueous, I'm not going to break it apart. The sodium hydroxide, though, this guy would break apart. It would break apart into Na plus aqueous and OH minus aqueous. Now, what does an acid and a base, when they neutralize, we have a neutralization reaction. We always make water, H2O, liquid. Liquids, solids, and gases do not break apart. And then we create an ionic compound that would be sodium. And then the negative part of this guy, like if this is the H plus, then the C2H3O2 must be the minus. So it's going to be sodium with the C2H3O2 minus. When an ionic thing is aqueous, though, then it is broken apart into the ions. So this would be like an Na plus aqueous, and then the C2H3O2 minus aqueous. This is the complete ionic equation. We want the net ionic, and that's where we get rid of spectator ions. Sodium has shown up on both sides. So what we're left with is HC2H3O2, the weak acid that did not break apart. Hydroxide, which is the strong base, Okay, that's cool. This alone gives just that information alone. Knowing that the weak acids don't break apart and the strong bases do, that gives you the answer to this. Aqueous. Then water has to be over there. And we're left with the conjugate base to this weak acid, the C2H3O2 minus aqueous. So that means our answer option is C. Okay, what is the maximum number of moles of aluminum hydroxide, not hydroxide, oxide, aluminum oxide that can be produced by a reaction of 0.4 moles of aluminum with 0.4 moles of oxygen? When you're given two reactants, like we're producing aluminum oxide from aluminum and oxygen, right? Like, here's my aluminum, here's my oxygen, and I'm making Al2O3. A balanced chemical reaction would require those coefficients. Now, we're saying that we have some amount of aluminum and some amount of oxygen. One's the limiting and one's the excess. And I have to figure out which one's which and how much of this aluminum oxide I'm going to be left over with. When we have limiting reactants, we need a BCCA table. B stands for before. Only moles in a BCCA table. So we had 0.4 moles of aluminum and we had 0.4 moles of oxygen. 0 aluminum oxide to begin with. Now a change is going to happen and then we're going to do a calculation. Reactants are minus, so this is going to be minus 4x, minus 3x, and products are plus 2x. So to calculate this, it'd be 0.4 minus 4x. This might equal 0. 0.4 minus 3x, that might equal 0. And then 0 plus 2x, which is just 2x. One of these is actually 0, the other one's not. So we have to calculate for x. So this would be 0.4 is equal to 4x. 0.4 divided by 4 is just 0.1, so x is equal to 0.1. 0.4 is equal to 3x, so 0.4 divided by 3, and we get x is equal to 0.133 repeating. Okay. The smaller the x value is the true x value. The bigger x value is not true. So this one equals 0. This one does not equal 0. And we know that x is equal to 0.1. So 0.4 minus 3 times by 0.1. So 0.4 minus 0.3, that means we're left with 0.1 moles of O2 that didn't react. And then x is 0.1, so 2 times by 0.1 is 0.2. That's how many moles of aluminum oxide we produced. There's our answer. 27. Okay, and I'm jumping to the end of this. Like, I see all this great information, but I want to know what it's asking first. So the question is, which element is being oxidized during the titration, and what is the element's change in oxidation number? So I don't need any of this to do that. So I'm going to write out my oxidation numbers. Now, normally, let's do this one first. Normally, oxygen is assigned a -2. That's what we get here. So there's 4 of them, but they're all -2. This whole thing is a -1, so the Mn had to have been a +7 to cancel out with the -2's to be left with a -1. So +7 -2. Okay? When an individual element is an ion, whatever the charge of the ion is, that's the oxidation number. If an element is in its pure elemental form, it's only oxygen or it's only hydrogen or only aluminum, it has an oxidation number of 0. When you have a peroxide, something to oxygen 2, that is the one time that oxygen, instead of being a -2, is actually a -1. So each of those oxygens are a -1, so each of the hydrogens had to have been a +1. Okay, +2 for that guy, -2 +1. Leo the lion says grr. And we want to know what's oxidizing. So losing electrons is oxidizing. All right. Hydrogens went from a +1, they stayed a +1. This oxygen went from a -1 to a -2.